This is part 3 of a 3-part lesson on oscillations and waves. And this lesson deals with traveling waves, resonance, and standing waves. All the images and figures that you see in this video are attributed to OpenStax College Physics, which is distributed by openstax.org under the Creative Commons Attribution License version 4.0. We just finished talking about oscillations or vibrations. And so the next couple slides are about the idea that if these oscillations or vibrations are connected to some external medium, they're coupled to some external medium, then these oscillations and vibrations can create waves that travel through space. So this slide is showing some examples of this. In the first part of the slide up here, we see a woman who is vibrating the end of a slinky. So her hand is vibrating up and down, but her hand is coupled to the end of the slinky, and this creates waves in the slinky that propagate through space in that direction. So this type of wave is called a transverse wave because the displacement of the medium through which the wave is propagating, which in this case is the slinky, is perpendicular to the direction the wave is traveling. What I mean by that is, in this example, the slinky is being perturbed up and down, but the wave is traveling to the right. So this is an important characteristic of waves. Waves are energy traveling through space, and in this case, this wave is being conducted by the slinky, but the particles in the slinky itself vibrate, move up and down in this case, but they don't move through space along with the wave. So the wave is energy moving through space, but the slinky itself stays put. All right, so here's another completely different type of wave. Here, the woman is holding the same slinky, but now she is moving her hands in and out. And this creates areas of compression and expansion in the slinky that travel through space. So these types of waves are called longitudinal waves, where the displacement is in the same direction as the propagation of the waves. So here the slinky's coils are being displaced left and right, creating these areas of compression and expansion, and at the same time the wave is traveling to the right. So a good example of a longitudinal wave is are sound waves. Sound waves are compressions and expansion of air. This slide showing waves on water, and you notice waves on water resemble transverse waves from the previous slide, and they're not exactly the same thing because water waves are boundary waves. They're waves that propagate along the boundary between two medium. In this media, in this case, it's water and air. But we can use this picture to introduce some concepts that deal with waves traveling through space. And the first concept is the concept of wavelength. And so for a traveling wave, this is the distance between successive peaks or valleys, essentially the distance between any point on the wave to the subsequent point in the wave that has the same size, magnitude, and also, in the case of this transverse wave, the same slope. So in this picture, an example of the way to measure the wavelength will be to measure from one peak to a subsequent peak, this distance right here. And we use the symbol lambda to represent wavelength. One thing to point out here is this seagull that's resting on the water, is floating on the water, is going to be perturbed up and down as the waves pass, peaks and valleys pass underneath it. But the bird doesn't move along with the waves. It vibrates up and down with the valleys and the peaks, the troughs and the peaks. So the seagull is being perturbed a distance 2x if the amplitude of the wave is 1x. So the amplitude of this wave is capital X. This wave is traveling, we can tell by this velocity vector right here that this wave is traveling to the right in this picture. which means the peaks are traveling to the right. And so another characteristic that we can define for a wave is how fast it is traveling. That would be how quickly a peak is moving through space. So we would define this as a speed, where speed is simply distance over time. And so we can write v for speed equals distance over time. And so here a natural distance to use when we try to quantify the speed of a traveling wave is its wavelength. And then all we need to know is how long it would take a peak or a valley of this traveling wave to travel a distance equal to 1 wavelength. So it turns out that this is the same as the period of the underlying vibrations or oscillations that are creating the wave. In the example here, it would be the amount of time it takes the bird to travel up to a peak and down to a subsequent valley or trough in this wave, and that's the period. So wave velocity can be written as wavelength divided by the period of the wave. Another property of traveling waves is that if you have two waves that are propagating through or along the same medium simultaneously, if those waves should happen to be at the same place at the same time, they will interfere with one another, or one wave will be superimposed on the other wave. Essentially what this means is that if two waves, for example, this wave right here, wave 1 and wave 2, were to exist at the same spot at the same time, they would essentially add together. You would add them together, and this would equal wave 3 down here, which is called the resultant. This wave, its value at any point in space, its size at any point in space, plus this wave's value or size at any point in space, gives you this wave, the values for this wave, the result at any point in space. So this is called superposition. Waves add together, and it gives rise to interference. This picture up here shows waves on a lake, and here you can see that there's waves propagating in and out of the picture and also left and right across the picture. So it creates this checkerboard-like pattern, and where the waves coexist at the same spot at the same time, you get interference. They add together. And the two most extreme types of interference are called constructive and destructive interference. So down here, we have an example of purely constructive interference. Essentially what we have here is two waves, wave 1 and wave 2, that look exactly the same. And in this case, they actually have the same amplitude, although that doesn't necessarily have to be the case. And these two waves have the same wavelength, and they also have the same phase, which means the peaks line up with the peaks and the valleys line up with the valleys. So when you add these two waves together, for example, if you add this peak right here to this peak right here, you get x plus x, which is 2x. So the waves add together and you get a resultant wave that is larger in magnitude, larger in amplitude. 1x plus 1x equals 2x. The other extreme example of interference is called destructive, completely destructive interference. And so this happens when you have two waves, and again, here we have wave 1 and wave 2 that have exactly the same amplitude, x, but here wave 2 is shifted. Its phase is exactly half a wavelength shifted relative to wave 1, which means this peak is shifted, this peak right here is shifted exactly half a wavelength in space relative to this peak in wave 1. So what that means is you have the peaks of, if we look at this spot, the peaks of wave 1 matching up with the valleys of wave 2. So this would be, if we look at just this spot right here, the value of the wave right here is positive x. The value of wave 2 right here is negative x. Positive x plus negative x gives you 0. So in this situation of destructive interference, the waves add together to give you a resultant that is nothing. the two waves, because essentially they're canceling each other out in space and in time, so you get a result that is zero. That's called destructive interference. Before we finish our discussion of standing waves, let's take a break and look at a musical instrument. This is a mandolin, a stringed instrument. And when I pluck the string, it creates a musical note, a musical tone. And there's a recognizable, each of these strings has a recognizable pitch. So what's happening here? What's creating this sound? Well, what's happening is when the string is plucked, those vibrations are coupled to the rest of the string, which creates traveling waves that travel up and down the string. But the thing about the string is the ends of the string, at least the ends, the part that's vibrating, are damp. They're fixed right here and right here on the bridge. The string is damp, so it doesn't move. So these vibrations can travel up and down a piece of the string. And when a vibration traveling this way, a wave traveling this way, gets to here, it's reflected, and it comes back this way. When it gets to here, it's reflected again. It goes back this way. So what you have is waves on the string which are traveling back and forth, back and forth, back and forth in a very special way where the ends are stationary. Okay. So one more thing before I put this down and we go back to the slides. Why? So let me pluck this string. Why does the pitch increase if I make the string tighter? And why does the pitch decrease when I make the string looser? All right, something to consider, and we'll look at the answer in a minute. So standing waves. With the example of the guitar, what I said was we have vibrations of the string that create waves that travel up and down the string, reflecting off of these fixed boundaries at either end. And what this causes is the establishment of what are referred to as standing waves on the length of the string. So standing waves are a situation where you have waves traveling in both directions along the same medium. So in the example of the guitar string, you have waves traveling to the left, waves traveling to the right, and these waves then have the opportunity to interfere with one another. In the case of this first panel right here, the waves are, it's a snapshot of the waves, one traveling to the left and one traveling to the right at the right. And it's a snapshot of these two waves at a moment in time where the peaks line up with the peaks and the valleys line up with the valleys. So you'll have completely constructive interference of those two waves, giving you a result, and that looks something like this down here. So let's call that t equals 0. So what happens is exactly a quarter period later, this wave has traveled a quarter of a wavelength to the left, and this wave has traveled a quarter of a wavelength to the right. So now you have a scenario where instead of peaks lining up with peaks, you have peaks lining up with valleys, which gives you completely destructive interference. And then exactly 1/4 of a period later, the waves have traveled to another spot where peaks and peaks line up, so you get constructive interference. And then another quarter period later, the waves have traveled to a spot where the peaks and valleys line up, giving you destructive interference, and the process repeats. So every period of the traveling wave, you get these alternating moments of constructive, destructive, constructive, destructive, constructive interference. And so what you have is these standing waves are really two waves that are traveling through space in opposite directions, but they give rise to these localized oscillations of the medium. In the case of the mandolin, it's a string that vibrate up and down. So these oscillations then end up to occur at fixed locations in space and result from alternating constructive and destructive interference. So now let's consider the guitar string a little bit more carefully. What makes the guitar string special in regard to waves that propagate along it is that both ends of the vibrating part of the guitar string are fixed. So if we think of those two blue lines as the ends of the guitar string, those two spots of the string are always fixed. They can never move. And we call spots that never move in a standing wave a node. So what this means is, the velocity of the wave that travels along the mandolin string or a guitar string is fixed by parameters such as the density of the string and the tension that it's under. And so what this means that only certain wavelengths and thus frequencies can exist along the length of the string. So before we move on, remember that wave velocity is wavelength over period. And we learned earlier that frequency is the reciprocal of period. Frequency equals 1 over the period. So we can write wave velocity, instead of writing wave velocity as wavelength lambda over period t, we can write it as frequency times lambda. So one more time, because the velocity of the wave that travels along the string is fixed by parameters like the density of the string and the tension that the string is under, and only certain wavelengths can exist along the length of the string as standing waves because of the fact that the ends of the string are fixed, then only certain frequencies can exist along the lengths of the string. All right, let's look at an example here. So in this first part of the figure up here, what we have is we have a wave that has a wavelength equal to lambda sub 1. And the wavelength of this wave is actually greater than the length of the string, which is capital L. But there's this relationship between the wavelength and the length of the string. The length of the string is exactly 1/2 the wavelength. And the reason this has to be so is because the ends of the string are fixed. So the ends of the string have to correspond with spots along the wave that have a value of 0. So the velocity of these waves that travel along this string is the frequency of these waves multiplied by the wavelength of these waves. And the wavelength of this particular wave is twice the length of the string itself. Wavelength equals 2 times L. So the frequency of these waves are the wave velocity divided by the wavelength, which is 2L. So it turns out that this is the smallest frequency or the largest wavelength that can exist as a standing wave on this string where both ends are fixed, because of this requirement that both ends are always nodes, these spots along the string where there is no motion. So we call this frequency the fundamental frequency. The next smallest wavelength that can exist along the length of this string as a standing wave is one where the wavelength is exactly the same as the length of the vibrating string. Lambda 2 equals L. But here the wave speed is going to be exactly the same. Wave speed equals the frequency of this wave multiplied by the wavelength of this wave. So the frequency of this wave that can exist as a standing wave is the wave velocity divided by L, which is exactly twice the fundamental frequency. So this second frequency of standing waves is equal twice the first, or fundamental. We call this the first overtone. And so what we see is that a pattern emerges. The next smallest wavelength that can exist along as a standing wave along this length of string with both ends fixed is one where the wavelength is 2/3 L, the length of the string. And the frequency of these waves would be 3 times the fundamental frequency. And we can summarize the pattern that emerges for the specific frequencies that can exist as standing waves along this string. These are the specific frequencies which correspond to specific wavelengths that have nodes at the ends of the string, is that the frequencies are integer multiples of the fundamental frequency, where in this case, need my pen, n equals 1, 2, 3, etc. And the fundamental frequency is wave speed divided by twice the length of the vibrating string. So the frequency of the nth harmonic is n times wave speed divided by 2L. So when n equals 1, we have the fundamental frequency, which is also referred to as the first harmonic. When n equals 2, you have the first overtone, which is also referred to as the second harmonic. And when n equals 3, you have the second overtone, which is also referred to as the third harmonic. So when I pluck a string on my mandolin, or if you pluck a string on a violin or any other stringed instrument, a guitar, you hear a specific pitch. But the truth is that when you pluck a string and create vibrations, the energy of those vibrations couple to the string and create waves that propagate back and forth along the length of that string, reflecting off the fixed boundaries at either end. And the frequency of the waves that can exist will follow this rule. So initially, there's energy at all different frequencies, but all the energy gets concentrated in waves that have frequencies fitting this mathematical rule. So why do you hear a specific pitch? Why do you hear a specific pitch instead of hearing all these frequencies? Well, the answer is usually many different frequencies are present when you pluck a string on a stringed instrument. But one of the frequencies dominates, and usually that dominant frequency is the fundamental frequency, or the first harmonic. The relative strength of the higher harmonics actually gives the character to the sound of the instrument. But the pitch that we perceive is usually the frequency of the first harmonic. So back to our final final question here is, why does tightening a guitar string increase the pitch of the sound it produces? Well, if you look at the equation governing the frequencies of standing waves that can exist on a guitar string, we see that the frequency, which of the fundamental, is directly proportional to wave speed. And if that is the pitch that we're hearing, the higher the wave speed, the higher the pitch, the higher the frequency of the fundamental. So it turns out that the velocity of a wave along a string, that is the speed of waves traveling back and forth on a string with both ends fixed, is, I lost my marker, my pen again, is equal to the square root of the tension under which the string is placed, divided by the linear mass density of the string, mass per unit length. So everything else being equal, a beefier string is going to have smaller wave velocities, which will give rise to lower pitches, lower fundamental frequencies. And as I showed you, as I tightened a string, increased the tension, that increased the frequency. And the reason is because as the tension increased, the wave speed increased. As the wave speeds increased, the frequency of the fundamental frequency also increased. So increasing tension increases wave speed, increases pitch on a stringed instrument. So this formula for the velocity of a wave along a piece of string is, I don't think it is in your textbook. I don't think it's in the OpenStax book, but it's an important one to know. So I've written it right here, add it to your notes. You may encounter this equation on exams. Wave speed equals the square root of the force of tension divided by linear mass density, mass per unit length. By the way, this L is not necessarily the same as this capital L, because this capital L is the length of the string that's vibrating, whereas this lowercase l could be the entire length of the string if what you know is the entire mass of the string. This is density per unit length, mass per unit length. So that concludes this unit on oscillations and waves. We learned about simple harmonic motion, masses oscillating on springs, the simple pendulum, and traveling waves, including standing waves, and we looked at the specific example of standing waves on a piece of string where both ends of the waves are fixed. And what we discovered is because the ends are fixed, only certain frequencies can exist as standing waves along the length of the string, giving rise to harmonics. So thank you. Review these videos as much as you need, and I hope you found them helpful.